Yes.
Okay, can I start?
Yes.
So, good afternoon, everyone. Now I'm going to give my final presentation of my project. The goal, as you all know, is to devise a robotic system coupled with non-destructive evaluation techniques, which can be used to examine large civil structures. The outline for this presentation will be like this. First, the literature survey, then the design of the robot, then the free body diagrams, and then the kinematic model, then simulation, and then we'll see the progress of the robot. Starting with some basic definitions, a robot is uh, an automated machine that replaces human effort, and a soft robot is a type of robot that is made of compliant structures similar to living organisms. Now here are shown some of the examples of soft robots. The one on the right is a clip uh, clip clamper, which is actuated electrically, and the one on the middle is also a clamper, which uses electroadhesion. The one on the left side is an artificial muscle, which is pneumatically actuated. Literature on robots in NDE. So the large civil structures need regular inspection, and the standard practices for these are pretty dangerous. And since the advancement of in robotics industry, deployment of robot for this task is being explored and tried. But there are some problems with the hard robots, like mobility of the robot itself, and also the non-uniformity in the civil structure. This is an example of a robot. It is made to detect concrete cracks in a tunnel, as you can see. So basically, to sum it up, there are problems with the normal robots, primarily of the mobility of the robot and also non-uniformity in the civil structures. Why soft robots? Well, soft robots can solve much of these problems. It is cheap, it is safe, and it has a compliant structure to take care of the mobility constraints. So my approach would be to make a flexible continuum robot fitted with ultrasonic sensor for non-destructive evaluation of large civil structures. Now, what is a continuum robot? A continuum robot is a robot with continuous backbone, much like the arm of an octopus, and has theoretically infinite degrees of freedom. For my own robot, I have taken an inspiration from the two robots. This is Techobot 2. As you can see, it is a continuum robot, and it has universal joints connected in series for its backbone, and there are strings that run along the periphery for the control of the robot. Next is the Festobionic handling assistance. It basically has a pair of uh, air chambers which can be pressurized or vacuum can be applied, and it basically takes care of the basic structure as well as the control for the robot. So after taking inspiration from these two robots, this will be the design of my own robot. There, it will comprise of an air chamber which can be pressurized, and it would be controlled by a bunch of strings that run along the periphery, around the periphery along the length of the robot for control, and there will be plates attached to it to which these strings will be attached. Now I have divided this into three sections. The three strings will run from here up to here, and this will be section one. Uh, the next three strings will run from the base up to here, and this will be section two. And the last set of three strings will run up to the last, and last will be the section three. Next, we start with the free body diagrams. This is the section three uh, of the robot. This is the last section from the base. And as you can see, uh, the load at the end is applied is P. The R denotes the reaction forces, M denotes the moment, and T denotes the tension in the strings, and W is the weight. And this was the XY plane, and similarly in the XZ plane. And the required equations are these. Similarly, for section 2, these will be the free body diagrams. These are mostly similar but with slight changes. This will be the required equations. And finally, section 1, which is at the base, and these will be the required equations. Now, after this, we will get to kinematics of the robot, but before that, I will introduce some basics of robot. Kinematics associated with robotics are basically two types, the forward and the inverse kinematics. So take the example of this two-link revolute joint manipulator. So it is of length L1 and L2, and angles are given as theta 1 and theta 2. So the forward kinematics would be that if I know the angle theta 1 and theta 2, I'm able to calculate the position and the rotation and the orientation of the robot. And on the contrary, the inverse kinematics would be that I am given the endpoint, say x and y of the robot, and I'm able to determine theta 1 and theta 2, which basically means I'm able to determine the orientation and position of the robot. So next is the transformation matrix. Transformation matrix is basically an operator in matrix form, which is used in mapping from one coordinate system to another. So it basically takes care of the position and orientation. Let's take these two coordinate systems, x, y, z, and x dash, y dash, z dash, and uh, let's say x dash, y dash, z dash coordinate system is at a displacement c from this coordinate system, and let's say that there is a vector p dash defined in x dash, y dash, z dash coordinate system, and we want to find the vector p which is in the xyz coordinate system. So how can you find that out? We can find it out with the help of transformation matrix. It's a 4 by 4 matrix, which includes the rotation matrix, which is a 3 by 3 matrix, and the displacement of the coordinate system. And basically is used in this form as it's basically used to uh, uh, put all the information at one place. So the vector p can be calculated as shown according to this formula. Now these coordinate systems are placed usually on different links. Let's say XYZ coordinate system is defined on the ground, and there is a link, there is a single link, and x dash, y dash, z dash coordinate system is placed on link 1 at the end. Now if I want to get the position of p dash, which is in x dash, y dash coordinate system, I'm able to calculate that in the ground plane according to this formula. So this is the last one. Now let's say there are two links. Now how I am able to get the vector p, which is in the o double dash coordinate system. So what we can do is find the transformation matrix from o to o dash and from o dash to o double dash, and we multiply together, so we can get the overall transformation matrix. And in this way we can find uh, the vector p, which was defined in p double dash, which was defined as p double dash in o double dash coordinate system. Now let's start with the kinematic model. The assumption that I'm taking are that curvature of each section of the robot is constant, and bending of one section of the plane will take place in a single plane only. This will be the setup of this will be the setup. This is the robot which is at a distance xd from the wall. This plane denotes the wall, that is zy, and there is a screen at certain distance from the coordinate system. And as you can see now, kinematic model in our case would be that in forward kinematics, I know the length of the strings and I'm able to calculate the position of the endpoint of the robot. And in the inverse kinematics, I'm able to find the length of the strings from the position of the endpoint of the robot. Now, the let's uh, now the kinematic model of a section. Let's assume that there is one section. There is a coordinate system attached on this section, and on the other next section there will be a coordinate system x dash, y dash, and z dash, and it is rotated at an angle phi. So how can we calculate the transformation matrix between these two coordinate systems? Now, as we had done earlier, we can define different coordinate systems in between these two. Let's say this is the coordinate system 0 and this is the coordinate system 4. Then we define different coordinate systems 1, 2, and 3, and we find the transformation matrix individually from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. And we multiply all these transformation matrix to get the overall transformation matrix, which is in terms of r theta and phi. So using the relation r equal to L by theta, we get the transformation matrix in terms of L, theta, and phi. Now this will be the orientation which the robot is desired to move. This is the O dash point, which is the uh, 0, 0, 0 point of the coordinate system. Then at a distance xd, there is a point O, and uh, at section after section 1, there is a point A, then B, and C, which will be the endpoint of the robot. Now, endpoints of the robot can be found by this transformation matrix. Let's say the endpoint is C, then we can find the overall transformation we can point C in terms of overall transformation matrix. Now we'll calculate the length of the strings in terms of these parameters L, theta, and phi. So for the section 1, the length of the strings L1A, L1B, and L1C. Similarly, for section 2, we'll get L2A, L2B, and L2C. And for section 3, L3A, L3B, and L3C. Overall transformation matrix for one section, L, theta, and phi. Now for simulation, what we can do is we can define the curve length S, and we can write the transformation matrix in terms of S, R, and phi, where R equal to L by theta. And if we fix L, theta, and phi for one section, we get the transformation matrix in terms of S, the curve length. Then the coordinates of the curve can be calculated as this. For coordinate of curve of section 1, we calculate this in terms of curve length S. This is all useful for simulation for forward kinematics for section 2 and similarly for section 3. Now this was the setup, and I have defined some uh, parameters like 20 up and 20 in the y direction, and similarly 45 and 45, and robot is placed at a distance 20. All dimensions are in centimeters. So I've selected some. I've calculated. I've selected some random lengths of the strings, and according to that, I've calculated that the robot will reach at these points, and I have simulated. The robot will go from P to Q to R and back to P. So let's watch this video. Here I'm interpolating the length of the strings, and that's why the path is somewhat curved. This is the point P, Q, and R, and it is going back to P. If we have interpolated in terms of point, then we would get a straight line. Now we'll start with the inverse kinematics. Inverse kinematics can be basically solved in two ways. The first one is the analytical analytical solution, and the second is the computational solution. Now, in our case, the equations were somewhat non-linear, so I was not able to find the analytical solution. So what I've done is the computational one. So firstly, I'm uh, defining some assumptions. So phi 1 will be 0, phi 2 will be 90, and phi 3 will be 0, and L1 and L2, L3 will be like this. They are basically interpolating as per the distance of the point, and the radius of curvature of second and third section will be same. So phi 1 equal to 0, which will basically mean that the section 1 will curve in the ZY plane only, and it will not move out, as you can see from this view also. And from here on, section 2 and section 3 will curve on this plane only, which is making an angle, say theta. As you can see, this the uh, orientation is circular. This is a diagram to show uh, how the section 1 will be calculated, and these are some of the equations. And as you can see, it is coming in terms of cos theta, sin theta, and theta. So I'm solving it using an inbuilt function in MATLAB, not analytically. And these are the remaining equations for the remaining parameters. And finally, I simulated in the with the reverse kinematics, and I'm selecting these random points. Let's see this video. So it moves from 30, 30 to 40, 35 to 35, 40 to 25, 40 and 40, 25. And here I'm interpolating the point x comma y, y comma z. So that's why the curve is also straight line. Now it's going back to the starting position. I've also made another video of these random points. I was not able to make more than 5 points because there was a bug in the I mean a bug in the code, I think. It basically traces out a square. So finally, the progress of the robot. This much is what I have made. Uh, I've tried it with a DC motor and it was able to pull, but I'm not sure with the speed control. And this is the Arduino. This is the motor driver, and this is giving 12-volt DC supply. It is connected from the home supply, which is 240 volts. And another image is this. Thank you. If you have any questions.